Every video you watch takes a journey. A file on a server gets split into pieces, copied onto machines near you, and handed to your screen one piece at a time. This is how that works. Start with the raw material. A camera captures light maybe 60 times a second, at millions of pixels each time. Uncompressed, a single minute of 1080p video is more than a gigabyte. An hour is over 100 gigabytes, and a movie is a terabyte before you press play. Nobody ships that. Raw video is so big because it is mostly repetition. One frame of clear sky is thousands of nearly identical blue pixels. And frame to frame, almost nothing changes. A person talks, the background just sits there. Compression works by throwing out what the eye will not miss. A codec is the rules for that throwing away. The oldest trick is the keyframe. One frame is stored complete, and the next few frames are only the differences from it. The encoder stores changes, not scenes. That is why a talking head compresses to almost nothing, and a sports field full of motion barely compresses at all. The family of codecs is an arms race over the same idea. H.264 came out of the year 2003 and is still everywhere, because it was the first one every device could decode. HEVC H.265 promised half the bits for the same picture. VP9 is Google's royalty-free answer. AV1 is the newest, strongest one, and it gives the best quality for the fewest bits, at the cost of being brutal to encode. The number that matters is bitrate. A good 1080p H.264 stream runs around 5 megabits a second. AV1 gets the same picture at about 2. That is the whole game, fitting the most picture into the fewest bits, because the bits are what travel over a network. But a codec is not a file. People mix these up constantly. A video file is a container, a box that holds the compressed video track, the audio track, subtitles, and timing data all together. MP4 and MKV are boxes. H.264 and AV1 are the languages the video inside speaks. You cannot tell what is inside an MP4 just by the name. It could be anything. The container exists to solve a simple problem. A stream needs to be written, read, and seeked with video and audio that stay in sync, so the box labels every piece with a timestamp. The video and audio tracks interleave, each chunk stamped with its time, and the player reassembles them as you watch. That synchronization is most of what a container does. Not all boxes are the same. MP4 is the internet standard, built for seeking and for editing software. WebM is the open one Google pushes, the pair to VP9 and AV1. MKV is the Swiss Army knife. It holds everything, but almost nothing official plays it. And for live video, there is MPGTS, a box designed for a moving picture, built from small packets that survive a noisy signal. The tool that moves video between all of this is ffmpeg. It is the hidden workhorse of the whole internet. Almost every platform, every editor, every encoder on Earth runs ffmpeg under the hood. One command can re-encode a video, strip the audio, repackage a file from MKV to MP4, or fix the timing. If a video moved from one format to another, ffmpeg probably did it. There is a subtle difference inside that tool. Remuxing is just changing the box, copying the tracks as they are, instant and lossless. Re-encoding is decompressing and compressing again, which changes quality and takes real time. Everything in this video is a mix of those two ideas. Now, the file exists. The question is how to get it to a viewer. The naive way is progressive download. The browser downloads the whole file in order and plays as it arrives. It works, but it has one fatal flaw. If the viewer's connection is faster than the video's bitrate, the download finishes early and it looks fine. If the connection dips for 1 second, the video pauses and waits. There is no middle ground. Adaptive bitrate streaming is the fix, and it changed everything. Instead of one big file, the video is cut into chunks, usually 2 to 10 seconds each. And it is not encoded once. It is encoded many times into a ladder of quality levels. A low bitrate copy, a medium one, a high one, all cut into the same time-aligned segments. The player is given a manifest, a small text file that lists every segment in every quality. The player is not a passive screen, it is the conductor. It watches how fast it is actually downloading, and it picks the quality for the next segment on the fly. Fast network, grab the high bitrate, network stutters, jump down a rung. The picture changes quality mid-video and you barely notice. That is the trick that makes video work on the internet. Video became plain HTTP. Every segment is just a file at a URL. Ordinary web infrastructure fetches it, caches it, and reserves it. HLS and Dash are just the two competing dialects of the same idea, Apple's and the open standard, and practically every site runs one of them. And this is why video needed an entire network of its own. One server cannot serve 1 million viewers. The upload is huge, the demand is simultaneous, and the same file gets requested over and over. So the platform copies the segments onto edge servers, machines in hundreds of cities around the world, closer to the viewers than any one origin could be. The player does not even ask the origin. When it looks up the stream's address, the platform's DNS answers with the nearest edge, based on where the request came from. The player connects to an edge a few miles away, not the data center halfway around the planet. Most of the time, the origin is never touched at all. That is because of the cache. A segment is small, it never changes, and it has the same URL for every single viewer. So 10,000 people watching the same film at the same quality request the exact same tiny file. The edge fetches it from the origin once and answers the other 9,999 requests from its own memory. The number the whole industry runs on is offload. That is the share of bytes served from the cache instead of the origin. Every byte that misses the cache is a byte the origin pays to send again. For video, where the audience is huge and the files are identical, a well-tuned cache offloads the vast majority of traffic, and that is the entire economics of streaming. The danger is the thundering herd. When a platform premieres a movie, every edge asks the origin for the same new segment at once. So networks add an origin shield, a middle layer that all the edges funnel through. The shield requests each new segment once and hands the answer to every edge that asked. One fetch instead of 1,000. That is the on-demand half. Now the harder problem. Live video has the same pipeline, with zero warm-up. The segment is written at the origin, and every viewer on Earth asks for it in the same instant. There is no cache to hit. The content is seconds old. That is why live streaming took so much longer to get right than video on demand. The live pipeline is capture, encode, upload, transcode, package, distribute. And the upload leg, called ingest, is the odd part. The camera pushes the stream up to the platform over the public internet, and that is a different protocol than everything else in this story. The oldest is RTMP, from the year 2002. It is a persistent connection where the encoder pushes frames continuously. It is ancient, and it is still the default. YouTube, Twitch, and Facebook all still accept RTMP today. Its latency is part of the industry's normal 30 to 60 seconds behind real time. SRT is the modern answer for flaky internet. It runs over UDP, so it does not wait for lost packets to be resent. Instead, it fixes them ahead of time with error correction, so a bad connection still delivers a clean stream. RTMP breaks when the upload stutters. SRT is built to survive it. The fastest ingest today is WIP, which is WebRTC, the same protocol as video calls. It reaches sub-500 millisecond latency, and OBS can output it natively. It is the reason a phone can stream live to a platform and still feel real time. But the trade is cost. It takes serious CPU to serve that to many viewers. Whatever the ingest, the server transcode is a one-way door. The platform re-encodes your upload into its own ladder of qualities, but it can only go down. A 720p source can never become true 1080p. What you upload is the ceiling on what your viewers can watch. That is why streamers obsess over their ingest bitrate. Live caching is a game of two clocks. The manifest is rewritten every few seconds, so it must be checked constantly, and it gets a cache life of about a second. The segments are immutable, they are cached for hours. The manifest moves fast, so playback keeps going, the segments stay cold, so the cache can fill. Get the manifest wrong, and the stream stalls for everyone. Every platform is the same machine wearing different clothes, so what each one actually runs is the real story. Start with YouTube, because it is the biggest. YouTube takes your upload and treats it as raw material. It is re-encoded server-side into a ladder of around 30 to 40 renditions, and the codec it picks is a business decision. H.264 for smaller audiences, because it encodes cheap. VP9, once a video crosses a few thousand views. And AV1, the most expensive to encode, mostly reserved for the biggest videos on the site. Google built a custom chip called Argos, just to make that cheaper. It is a transcoding engine built to decode and re-encode at enormous scale, and it is why YouTube can offer AV1 to huge audiences at all. The cost of encoding was the barrier, and they engineered the cost away. Then delivery. Google puts its own cache, called the Google Global Cache, inside internet service providers. The viewer's own network serves most of YouTube, so roughly 95% of the bytes never leave the building where the viewer lives. That is not streaming magic, that is a CDN owned by the platform sitting inside your ISP. TikTok is the same idea with a different shape. It accepts MP4, WebM, and MOV, encoded in H.264, HEVC, VP8, or VP9, at 23 to 60 frames per second. For short vertical clips, it often skips the full re-encode and serves your file near as it was, trusting the fast edges. The algorithm is a separate giant system. The delivery is just segments on a CDN like everyone else. Twitch is where live got solved in public. You push RTMP to an ingest server chosen by a system that routes you to the healthiest edge. Twitch re-encodes your stream into its own ladder with a custom transcode fleet, packages it into HLS segments, and serves them over its CDN. Low single-digit seconds of latency, and it was the model everyone else copied. And the most telling detail is the chat. Twitch chat is a completely separate system from the video. It is a real-time messaging layer over its own connections with its own clock. That is why chat can run ahead of the picture. They are not the same stream. They are two different planes of the same platform. So the whole journey is one loop. The camera produces an absurd amount of data. A codec throws away what you cannot see. A container boxes up what remains. The platform re-encodes it into a ladder and cuts it into segments. CDN edges cache those segments near the viewers, and the player conducts picking quality on the fly while the cache does the heavy lifting. Every tap on a video is really a request for a few small numbered files from a server a few miles away. The one massive movie you think you are watching never exists as one file at all. It is thousands of tiny pieces, each fetched by a player that knows exactly which one it needs next. That is how streaming actually works.